on to those who are doing the statistical analysis on this, because I'm not a statistician, I'm not a PhD statistician, but I know that these issues are often debatable, even by PhD statisticians. My background in statistics is that I'm a nuclear engineer, so I've dabbled in statistics, and at General Atomics in San Diego, I was there for 24 years. I did manage a statistics and measurement control group for about 5 years, which did involve me in statistical analysis. And so that's where we are at this point. This will be released for general distribution as soon as we are able to respond to all of those who have done critical analysis on it. So with fear and trembling, I'm going to continue here and put this out on the floor for consideration and distribution. Or do we have any PhD statisticians in the audience? Okay, so I can get away with this. Okay, good. Okay, now, the previous individuals who have done statistical analysis on the carbon-14 dating, Remy Van Holst, I'm not sure if I'm pronouncing these names correctly, Brian Walsh, I've been in communication with him. He has reviewed it. I've not been able to respond to him. I was so busy working on something else called Shroud Conference 2017. And then the very detailed paper by Riani, Atkinson, Fonte, and Grosilla. By the way, we will be showing that on the last part of the dinner hour. Here, we'll be showing it over in room 2, and this is quite detailed. It'll be a challenge to your thinking. So toward the, I think it's 5:40, it's going to be starting over in room 2. You're welcome to join us over there. So what I'm saying is going to be a little bit of background with the terminology and the approach that they take in their more detailed analysis. So what I'm going to show you today in no way is inconsistent with the conclusions that they reach. I reach the same conclusions that they do, only I'm taking a bit more of a, especially relative to Riani, etc., a little bit more of a simplified approach, and one that I'm hoping that I can explain to the layman. How do you like that? Okay, now, what is carbon-14 dating? Okay, we are not progressing here. I'm sorry, I'm on page 16, and that's page 13. Okay, this is not progressing. This thing is not progressing it. Okay, hold on. Slideshow. I go to slideshow from the current slide. I'm sorry, this is not responding. I'm running off of Microsoft PowerPoint. Okay. Now, and I'm not sure why that was on there.
Is that yours?
Yes. This is Wade. Let's give a hand for Wade, okay? He's been doing our audio. Thank you. There we go. Okay, let's see if we can. Okay. Thank you, Wade. Okay, so that's where we were. I've done this. These are the different authors, Remy Van Holst, Brian Walsh, Marco Riani, Atkinson, Fonte, and Grosilla. Okay, good. This is the figure that explains what carbon-14 dating is. So in other words, when a plant is growing, such as flax, which is then cut down to be made into linen, what we show here, okay, can you see the laser pointer there? While the plant is growing, let's call it 100% of full carbon-14 content. Because the carbon-14 that would be in the flax while it was growing, it would be decaying with a half-life of 5,730 years, so it would be gradually disappearing, but the plant is also taking in new carbon from the environment in photosynthesis, including a certain very small fraction of that carbon being carbon-14, so that the new carbon-14 being brought into the plant while it's growing is just compensated by the carbon-14 that's decaying. But as soon as that plant is cut down, it dies. And so photosynthesis is no longer being done. So at that point then, you only have the carbon-14 decaying. It's not being replaced by new carbon-14. So this decay curve is the half-life. That is, in 5,730 years, you would only have 50% of the original amount of carbon-14 remaining. That's the curve for carbon-14 decay. So that when they took the sample from the Shroud of Turin, what they measured was about 92% of what they thought should be there. In other words, instead of 100% carbon-14 that they thought should be there, they measured 92%. So they came over on this curve, just horizontally over and down, and they said, well, gee whiz, that sample is only 700 years old. Okay, consistent with 1260 AD. That's what they did. Okay, let's move on. It looks fairly simple, doesn't it? We'll go into some of the assumptions, underlying assumptions behind this methodology. Is carbon-14 dating accurate? That's what I'm always asked. Well, it's accurate if the assumptions that are underlying the methodology are true. That's how I always answer it. So that pushes the question back as to what are the assumptions involved, and are they true? So that one assumption here is that there's been no dramatic change in the carbon-14 since the sample was cut down and died. It's just only decreased due to the natural decay of that carbon-14. I'm sorry?
As opposed to what else would change it?
Multiple things could change it. What if some acid came along and preferentially washed out carbon-14, more carbon-14 than carbon-12 or carbon-13? Okay. We are still having trouble here. Okay, we'll go this way. Okay, so now the samples on the carbon-14, okay, were taken right from this corner. Here's the front image. They were cut right from here. So this would be, as you hang it up and you're looking at it straight on, this would be the lower left-hand corner. This little piece right here is not the shroud. That's the backing cloth that you're looking at, where a piece of the cloth had already torn off. Now on the next one, we can see a little bit more detail here, so that this is the backing cloth that you're looking at. This is called the side strip that was evidently cut off and then reattached with that seam, so that the cut in 1988 was along this line like this. And from that piece, they cut what we call A1 to go to Arizona. They then cut Z to go to Zurich, Switzerland. They then cut O to go to Oxford, England. And then they realized that this piece, the A1, was smaller than either one of those two. So they cut another piece, let's call it A2, to go to Arizona. So Arizona received A1 and A2. This piece had a very important function. That was to go into the pocket of the person who cut it. Okay? It's amazing how things happen. Okay, let's move on. There's a picture of him cutting the cloth. Okay, so then the statistical analysis was published in the British journal Nature, coming out February 16th in 1989. That journal, that issue of the journal included actually two things, and one of them was radiocarbon dating of the Shroud of Turin by P.E. Damon and a host of others. And so this statistical analysis is often called Damon, and I will do so. Now, and this is available from shroud.com. The other thing that actually came out in the same issue, in the letters, was an observation by an individual who said that such a date should not be trusted because there could be, have been a neutron emission involved in the Shroud of Turin, which would have shifted the carbon-14 date, and we'll get to that. Okay, so now these numbers are probably too small. This is in my document, but I just point out, we'll get an enlargement of this in just a second, so that they tested not only material 1, which was the Shroud of Turin, but also materials 2, 3, and 4. These were the standards that were taken from other sources. Number 2, material number 2 was the linen from the tomb of so-and-so in Egypt, 11th to the 12th century AD. Material 3 was a mummy from Cleopatra from Egypt, 110 BC to 75 AD. And material 4 was the cope of St. Louis of France. And it gets a little bit small for me to read. 1290 to 1310 AD, so that they were running the Shroud of Turin against 3 other samples, 1 from the 1st century and 2 from the Middle Ages, okay, just to bracket that information. I'm sorry. Okay, so this is an enlargement of the bottom portion of that last slide. And what we show here, let me back up one. Not only do we have 4 different materials, but these are the values that were obtained by the 3 different laboratories. All 4 of those samples were sampled and sent to the 3 different laboratories in Tucson, Arizona, Zurich, Switzerland, and Oxford, England. And those are the individual measurements that were made. So let's go down and we'll take a closer look at the results. And so what we see here, statistical analysis listed in Damon. This was in the British journal Nature, after I think it was about 23 different individuals signed off on it. And so what we have here, we don't need to spend too much time on materials 2, 3, and 4. We'll make some observations. But material 1 is the Shroud, so we're going to make most of our observations on that. And so we come down and we have average values being reported by each of the different laboratories. You see the average value here is 646 plus or minus 31 years. This is called a 1 sigma value, so that 67% of the probability that the actual value will fall within 646 plus or minus 31 years, and so on for the other samples. And so what they did was that they did 2 things. First of all, they believed, and let's see if we can, okay, they believed that they should be able to weight these results by the uncertainty and thus come up with this line, a weighted mean or average. Statistical analysis term for average is mean. So 686, 689 plus or minus 16 years, 397 plus or minus 16, etc. And then from, okay, from this data, you notice this is bold. You see that? You see this? This is bold up here. Now, what they assumed that they should be able to do was to be able to calculate the weighted mean based upon the uncertainties that were given to them. And when they did that, they obtained this line, but they didn't like that value, the plus or minus 16, because things didn't make sense with this value. So they said, okay, for material number 1, we don't like the results. We're going to ignore it. And so they then calculated, ignoring those uncertainties, and just calculated the mean and the uncertainty from the values, ignoring their uncertainties because they wanted to. Okay? I'm sorry, I don't mean to be unkind here, but this is not good science. Okay? This is My term is fudging the data. Okay? Now, so when they calculate this value, they use a chi-squared analysis on this data. Kevin, you correct me if I'm saying anything wrong here. Okay. So they took these values, calculated using a chi-squared statistical analysis, and that's exactly what I've done in my later calculations. They obtained a certain value. They then used that value to calculate a significance level, and let me try and explain that to you. This significance level on the bottom here calculates the probability of that average value being consistent with the reported values from each laboratory and the statistical uncertainties that are given. And so what you see here for material 2, there's a 90% probability that the measurement, the random measurement errors give a consistent value between the result and the original data. So in other words, they're saying that this material is consistent with all of the measurement variations being random measurement errors. You know, a little bit high, a little bit low. And you really don't care because it can be calculated or assumed to be a Gaussian or a bell-shaped curve. So we have a 90% here, we have a 50% here, a 30% here, all fairly reasonable approximations to these values being consistent with the original data. But in Damon, they didn't like this value at all, so they went to this value in order to get this up to 5. Now 5 is kind of a criteria, okay? Now if you went to the horse races and you saw 2 horses were going to run in the next race, and they looked just as good one to the other, but God tells you the horse A has a 5% chance of winning. Now there's only 2 horses racing, and assuming you want to win money, which horse are you going to bet on? I hope you say horse B, because if horse A has a 5% chance of winning, horse B has a 95% chance of winning. So what this is saying is that the option where there's only random measurement error has a 5% chance of winning. So the other option where there are also systematic biases affecting all of the measurement data has a 95% chance of being true. And that's what they're ignoring. Didn't want to go there. I'm sorry. Am I saying anything wrong, Kevin? No? Okay. This is amazing, isn't it? With 23 people signing off on it. So we have the average values here, the average mean. They chose the higher value of 31. Now, this would be called the uncorrected value. First of all, it's BP, before present. They have to define what their starting point is for all the years. So 1950 is kind of their starting point because they couldn't define it as starting before today because every year today moves by a year. Okay, so they define it relative to 1950. So those are the ages BP, before present. But let's move those over to AD. Now that's something we're more familiar with. So this is where they come up with the raw value of 1260, simply by essentially averaging those 3 values. And so that's the uncorrected or raw value or a radiocarbon age. They then take that and correct that using a curve that results from tree ring counting, and carbon dating of those tree rings in order to correct for changes in carbon-14 production in the upper atmosphere and elsewhere that affects the carbon-14 concentration down where we live and where the plants live. So the 1260 then becomes a range of 1260 to 1390. These 2 values being 1260, that's just the luck of the draw. It just happens to turn out that way. Normally it would not, but in this case it does. So if you take the average between those 2 is 1325. Sometimes you hear that. The raw value that I like to use is the 1260 value, because otherwise it gets very complex. Okay? So what we have here, now, I know the carbon-14 dating is wrong. I don't know about you, but I do. Okay? Now, how can it be wrong? Well, if I just reach in my pocket here, let's see if I can get it. I carry this just for such a time as this. Okay? And in here, thank you, Harry. This was bought for me off of eBay. Should we tell them how much we paid for this? You paid for this? No. Okay. This is an authentic Byzantine coin with the image of the Shroud of Turin on it. And you can see the front here and the back. Here's the image of the image from the Shroud of Turin. This is an authentic Byzantine coin from the joint reign of Basil II and Constantine VIII. The date is 1025 to 1028. Now, the significance of that is that that's 235 years before the extreme range given to us by carbon-14 dating, 1260. So that this does two things for us. Now, usually, only the first is recognized. So that the first item that you ought to recognize is that this shows that the carbon dating is wrong. It's flawed. But there's a much more important issue that this shows. This raises the very serious question, how could the carbon dating be so wrong? And that's a very serious question, because we're dealing with very precise equipment that gives you very small uncertainties. Yet it's entirely wrong. How is that possible? So that's another mystery. How can the carbon dating be so wrong? Let's move on. Okay. So these are the individual values that were obtained, the dates AD reported in Damon. So at Oxford, 3 different measurements giving this average. Zurich, 5 measurements giving this. Arizona, 4 different measurements as reported in Damon. Oh boy. Now, we'll do a little bit. Well, let's look at this. And let's look at some of the anomalies just in this data. Okay, there are anomalies in this data. Let's see if we can find them. First of all, you see these 3 values? Average of about 55. 30, when you combine that, it forms the uncertainty of about 30. In other words, the uncertainty is reduced when you combine multiple measurements. Same thing here, only we have more measurements so that the uncertainty is reduced more. What about over here from Arizona? It's not. How can that be true? Why is it that way? Secondly, let's see if we can go on. Okay, possible problems with the data. So the uncertainties appear to be inconsistent within the data. And that's very important because you realize that the uncertainties are based on measurements of standards that are being made at the same time that the samples are being measured. So if you disbelieve the uncertainties, you ought to disbelieve the measurements. How can you believe one without the other? Because they're being made on the same equipment at the same time. Also, the range of the mean values appears to be too large for the stated uncertainties. Let's take a look at that. So in other words, if we look at these values, 1200, 1274, or 1304, and then we just take the 2 extreme values. That is the Arizona value, 1304, the Oxford, 1200. And we take the Damon stated uncertainties that they list in the paper, plus or minus 31, plus or minus 30. Okay, let's just do a straight subtraction. This is basic statistical analysis, okay? So 1304 minus 1200 is 104. But when you combine these 2 numbers, they have to be combined statistically, which means that you square the 31, you square the 30, you add the 2 together, you take the square root, you end up with 43. So that in doing this subtraction, it's 104 plus or minus 43. Now that's important. You have to believe, if you're going to believe the values, you have to believe the uncertainties. But let's look at this. When we take a look at 104 divided by 43, 104 divided by 43, that is, this difference is 2.41 times the uncertainty. That's greater than 2. 2 is the normal criteria for rejection. Okay? So based on this, we should reject this data as coming from the same sample. In other words, this proves that the sample sent to Arizona and the sample that sent to Oxford were basically different. How could they be different? Why are they different? We can't just ignore it by saying that these uncertainties must be understated. No, this is science. You can't just assume something because you want to. So the conclusion, the samples tested by Arizona and Oxford were basically different. Let's go on. Now, let's take a look at Tucson's measurements. Tucson, in Damon stated that Tucson did 4 measurements. Not true. This was found, how many years later was this discovered, Mark? 1989 is when they published the 4 values. Did we know at that time?
Donnie Hughes sends a letter to the other radiocarbon.
Yes. It was. I didn't know until maybe 18 years later. Confirming it.
We never found out till well into the 90s or after.
Yes, it was many years after that we people investigating the Shroud found out it wasn't 4 values, it was 8 values. This was a document signed off by how many? 22, 23 individuals? And yet this was not true at all. My goodness. So these are the 8 values that were measured. And you notice when they reported them in Damon, what happened here was that the smallest and the largest value were eliminated from the data by averaging. Isn't that amazing? This is what I call a fudge. You know? I mean, they wouldn't like me for this, but I don't see how you get around it. This isn't right. The actual measured data, we look at it here. We have 8 values from Arizona. Now, when I do this calculate, this is the Damon values down here. This is my calculation starting from those values. So what I calculate for Oxford is in good agreement, for Zurich is in good agreement, but look at Arizona, instead of 31, it's 17.2. Because there's more values. The more values that you're bringing together, the better agreement you would have. You would expect to have the greater confidence that you would have in the overall average that you obtain. So a simple analysis using my values, using this value of the 17.2. So then we do the same analysis here. 1303.5 minus 1200.8, that's 102.7. This, again, combines statistically into 35.2. Now, instead of being 2.41 sigma difference, it's 2.92 sigma difference, making the argument even stronger that these 2 samples were basically different samples. We're now almost 3 sigma away. Okay, so this is the uncertainty that I calculate on this one. So this is the value and the stated and the calculated uncertainty. And so what they did in obtaining 5 minutes left, isn't this amazing? So that what happened here was that they gave a 1260 date, whereas this plot fits the data. Their approach only goes through 1 data point out of the 3. Do you see the difference? So, what is it that would cause this slope to be true? You know, the question was, how could the carbon dating be so wrong? We see part of that question is, how could Oxford and Tucson be so different that this slope fits the data, whereas the Damon approach does not. We're going to have to speed up. I'm sorry. I'm on 33, and we have quite a ways to go here, okay? So, why do measurements vary? There's two causes for measurements to vary. There's random measurement error, and there's the other approach is a non-random something that's causing the measurements to be off entirely. Like if I took off my watch, not this one, my other one, and had 16 different people read the time, you could get a slight variation on how people read the time, right? That'd be the random measurement error. But the point is that the watch hasn't worked for years, so that it would be basically wrong due to a systematic bias. It hasn't worked for years, okay? So that's the difference between a systematic, something that's causing the measurement to be off, and just random measurement errors. But these non-random variations, it's called, in statistical analysis, it's called systematic bias. It can affect all of the measurements. So a random measurement is usually assumed to be a Gaussian distribution. You assume that to be the case for random measurement errors. That way you can deal with it mathematically. You don't need to sort out exactly what the cause is. You can just proceed. Meanwhile, typically, systematic bias is ignored because it's difficult to deal with. Okay, let's consider, tell you what, I had a simplified example here, and gee whiz, we're going to ignore all that. And, okay. Now, statement in Damon here, the underlying principle of the statistical analysis had been to assume, unless there is strong evidence otherwise, the quoted errors reflect all sources of error, that weighted means are therefore appropriate. Nice statement. That's a good statement. Yet, what value is it when they can't keep it? They applied this to samples 2, 3, and 4, but they didn't like the result for sample 1, so they ignored it. But they did admit the range of the sample values was with 95% probability with the stated random measurement errors. In other words, it's not just random measurement errors that are affecting the measurement values. There's a high probability that there's something else affecting it. At that point, they should say, we're going to pull back, and we cannot make any statement regarding the dating of the Shroud, because there's something else going on here that we don't understand. Now, that would be the scientific approach, but they didn't do that. Now, we're going to proceed here, and okay. When I go back with the new data and calculate these values, it's not 5%. It's actually 4.18% probability of it being random measurement errors alone. They rounded 4.18 up to 5. Is that how you round? Okay, why did they do that? Because this value was below their criteria of 5%. And I don't myself, I would rather bet on the horse with a 95% probability than the horse with the 5% probability. I think it's kind of an arbitrary thing to say. Okay, let's move on. So when I then go back, not just starting from the average values, but go back to the basic data, and I recalculate it, it's not 4.18%, start going all the way back to the original data, it's 1.39%. What is that saying? That's saying that the probability of the average value being the result, and the variations of all the measurements being consistent with random measurement errors alone is only 1.4%. So therefore, the probability of there being significant Biases, something has changed the measurements with a probability of 98.6% probability. So, skip that. We're going to skip that. Okay, I've shown you this already. Okay. Probably. So, Damon used a chi-squared statistical analysis of whether the three laboratory average values are consistent with the individual measurement uncertainties. He reported a 5% rounded up value. The correct value without rounding is 4.2%. So he rounded up from 4.2 to 5% to get up to his criteria, their criteria. But a chi-squared calculation of all 16 measured values was only 1.4% probability. So the probability that measurement variation is due to random measurement errors alone is only a 1.4% probability. Therefore, the probability of random measurement errors plus a systematic errors or bias, that is, something causing all of the measurement values to be wrong in a systematic fashion, something is causing them to be wrong, is 98.6% probability. Something probably affected all the measurement data. That's it. Thank you. Yeah, we do have time for questions, or do we?
It's your show.
Yes, it's my show. You're the moderator.
Well, this isn't working. Let's see.
Mine works. Kevin, any questions? Yes, I hope we aren't getting any. I'll tell him that Kevin told me to say it. Question. Why was it so on? It just, it was on in the sense that when they averaged the three different values, it came back to about the average. And that was the middle value.
But it was still saying that the Shroud was pretty recent, 1200.
What I'm saying is that every measurement they did was affected by something. Okay? And I'll tell you what that is in the next presentation.
Yes.